I'm Professor Christian Euler, and today I'm going to tell you a little bit about my research interests. So there are a number of grand challenges that humanity faces today. Climate change, driven by excess CO2 and other greenhouse gas emissions, the accumulation of plastics in the environment, and the depletion of the finite resources required for manufacturing are some of the biggest of these. In the face of such challenges, there is an urgent need to find new, sustainable, and minimally impactful ways to make the chemical products we use every day. These products are things we often take for granted, like plastics, coatings, adhesives, etc., that all contribute to our quality of life, even when we don't notice their role in our day-to-day. My research focuses on engineering biological systems to address these big challenges through biomanufacturing. I consider how we can use our challenging waste streams, like CO2 and plastics, as feedstocks for novel, scalable bioprocesses, which make use of microbes engineered to produce chemical products. To do this, I look at the wide expanse of biochemistry that exists across the tree of life and that which is being developed in the lab, and I build new-to-nature metabolic pathways from it. These pathways will allow microbes to efficiently transform CO2 and its reduced derivatives, like formate, ethylene glycol, and acetate, into things like biopolymers that can be used to make biodegradable plastics and solvents that are required to produce construction materials. I work with other researchers on integrating these bioprocesses with electrocatalytic processes that can reduce CO2 using renewable electricity. I use a similar approach to build bioprocesses that can recycle plastic waste, such as PET, into other high-value biodegradable polymers. Globally, less than half of all PET plastic is recycled, and as a result, much of it ends up in the ocean in the form of microplastics that are ecologically disruptive. There is little economic incentive to recycle PET plastic today, but this could be changed if it could be recycled into a more valuable product. So, I build biosynthetic pathways that transform the degradation products of PET into polymers with higher value than the feedstock, and I combine these with emerging biochemical breakdown pathways for PET plastics, mediated by a new class of enzymes called petases, to move toward a circular plastic economy. All of the work I do is geared towards scalability and technology transfer. My philosophy is that these grand challenges will never be solved unless we ensure that what we do in the lab has meaning in industry.